Year 12 chemists, welcome to TP's Chemistry Cuts. In this video we look at factors that cause changes to chemical systems at equilibrium. We start by introducing Le Chatelier's principle, which we then use to predict the effect of first changes in concentration of reactants or products and then pressure. Along the way we note that these changes do not cause the value of Kc to change.
Equilibria apply to reversible reactions. These are reactions where reactants form products, but then the products react together again and reform reactants. And so there's this backwards and forwards idea. And each of those reactions, the forward reaction and the reverse reaction, has associated with it its own rate. And when those two rates are equal and opposite, then it appears that there is no reaction going on anymore. The concentration of reactants and products is now constant. So for all intents and purposes, it appears that the reaction stopped. In fact, it hasn't. There's still a forward reaction going on and a reverse reaction. They're just cancelling the effect of each other out. So we say that equilibrium is a dynamic process. And then we introduce the idea of an equilibrium constant, which gives you some idea of where equilibrium lies. In other words, what's the concentration of the products relative to that of the reactants. So the larger the number for the equilibrium constant, it's telling you you've got a higher concentration of products relative to reactants, and so on. We looked at the single condition that must be met for equilibrium to be established, and that is the system must be closed. In other words, nothing should be allowed to get in and nothing should be allowed to get out, and that's a closed system. Okay? Now, what happens then if we change things? In other words, we open up the system briefly in some way. What does that do to equilibrium? And how does that affect the relative proportions of reactants and products? And that's what we're going to find out next. And that's using Le Chatelier's principle. Okay? Now, it's really important you understand that Le Chatelier's principle is just a predictive tool. It's not an explanation in any way. It just allows you to predict what's going to happen if you change things. Okay? So I've written it on the board, and I'll give you a chance to copy that down if you want to do so now. Okay. So what it's saying there is that if you make a change to a system that's in equilibrium, then equilibrium shifts. You've lost equilibrium, so it's going to shift. Okay? And it shifts in a way that minimises or attempts to minimise the effect of the change. Now that won't mean an awful lot at the moment, but it's something that we will unpack bit by bit using concentration, changing concentration as an example. Okay? So, and the important thing to note here is the only reason that equilibrium is being affected at all is that we are no longer having a very short period of time, the system is no longer closed. Okay? So there's a very simple approach to this. The first thing you need to do, and this will sound very familiar to something we've done previously in collision theory, rates of reaction in collision theory, is what is it we're doing when we make the change? Okay? You're adding a reactant, but how's that affecting our system in equilibrium? When we consider the equilibrium constant, the answer is you're increasing the concentration of one of the reactants. So why don't we write that down? So what you're doing is you're increasing the concentration of that reactant, and if you then recalculate what would be Kc, you find that Kc has changed. Okay? Which means that equilibrium's changed. Well, it can't. Equilibrium stays where it is. That's the whole point. And so equilibrium's been lost because you've opened up the system. Now we can apply Le Chatelier's principle. And what it says is it's going to shift equilibrium in a direction that minimises the effect of the change. So if we've increased the concentration of a reactant, we want to decrease it. So we're going to shift equilibrium in the direction of a forward reaction. Okay. So what I've written there is it's trying to minimise the effect of the change, because that's what Chatellier's principle says it's going to do, and it's going to push equilibrium to the products, because you've put in reactants. It's going to try and take them away, make it smaller. And so the wording we use is it's going to favour the forward reaction. What it means, it's giving priority to the forward reaction over the reverse reaction. And if you do that, you're going to shift equilibrium across. Okay? Does that make sense? So the effect of favouring the forward reaction is equilibrium So let's go back to KC. What we've done is we've added a whole load of reactant, so we've increased the concentration of a reactant. So what we've done the equivalent of is we've increased the denominator part of KC. So the value of KC has gone down. Chatellier's principle is telling us it's going to minimise the effect by favouring the forward reaction. By favouring the forward reaction, the concentration of reactants is then going to go down, while the concentration of products is going to go up. So the KC value will go back up. And it will go back up to exactly the same value that it was before you opened the system up. And that's a really important point, that when you make changes in concentration, when equilibrium has been restored back to where it was, where there's no more changes going on, and you recalculate KC, you'll find it has not changed at all. Okay? So any changes to concentration have no effect on the value of KC once equilibrium has been restored. Okay? Because you've lost equilibrium, it's restoring it, you've increased the reactants. The effect of Chatellier's principle has been it's brought the reactants back down, pushed the products up, and so you're basically restoring KC back to its original value. Okay? So this is in brackets because it's making an important point, but you don't have to explain this every time. So that's one of the big take-home messages today. Okay? Whatever you do in terms of concentrations to a system in equilibrium, when it's restored to equilibrium, because you lose equilibrium the moment you add something in, because you've no longer had a closed system temporarily, so equilibrium's been lost, it's got to restore it. Once it's been restored, then if you recalculate KC, it'll be exactly the same value. And that is a really important point. What it's telling you is the absolute position of equilibrium is not affected by changes in concentration. It's fixed. That's what the equilibrium constant is telling you. Okay? It's an important point. So I'll go through it again just to make sure you get the idea. Increasing a concentration of a reactant temporarily means that the KC value, because you've increased the denominator, the denominator, which means the KC value, if you want to call it the KC value, has gone down. The Chatelier principle is applied, so you're favouring the forward reaction. It increases the concentration of products, reduces the concentration of reactants in an attempt to minimise the effects of the change you've made. And what that's doing is pushing KC back up again, because you're increasing the numerator, the products, you're decreasing the denominator, which is the reactants, and so what you've done is you've pushed it off kilter. It's coming back onto the same position where it was originally. So it's like one of those, those little dolls with the round bases. You push them off and they come back to the original position that they are. Okay? So that's the really important part of this. Yes?
So you said this is like merely theoretical, right?
Sorry?
The idea of it's relatively theoretical, right?
No, this is not at all. This is just a predictive tool.
So this is so what you're saying is like the reactants you enter and they kind of balance out.
So you add in reactants and it's just basically pulling it away as much as it can, so it can restore KC back to what it was originally.
But at the end of the day, you've still got more reactants entering.
you've got more of one of the reactants. What you're doing is you're unbalancing the relative proportion of the two reactants. So you're suddenly adding in one. They're no longer, say you start with equal quantities, you suddenly add one in extra, and that's unbalanced the amount. So it'll try and reduce both of them at the same time, not just the one. Because when the reaction occurs, it's reducing both reactants, isn't it? Okay? It's a thing to lose track of very easily. Because you would immediately assume when a reactant is added, you're actually adding, if there's two, the same amount of each. You're not. You're adding one. Okay? What I could do now is just go through the alternative. What happens, and you can do either remove things or add things. It doesn't matter. What you've got to see is what is the effect of what you're doing on concentration. Okay? So let's say we remove a product. If we remove a product, and there are ways of doing that from the system, what is the effect on concentrations if you remove a product? In its simplest form, what are you doing? Removing a product. You're decreasing the concentration of one of the products, yeah, or the product itself, if there's one product. So if you decrease the concentration of a product, Le Chatelier's principle says it's going to react in a way or respond in a way that's going to try and minimise that. So it's going to try and push it back up. So you've removed a product, you've decreased its concentration, so it's going to try and improve the concentration, put it back up. And the only way it can do that is favouring the forward reaction. So it's going to react together reactants to make more products, so the concentration will go back up again.
So it's always going to...
Always the opposite to what you do, the system will try and put back. So if you take something away, it'll put it back. If you add something, it'll try and take it away.
So it always favours the product?
No. How would we actually get it to favour the reactants?
By adding more products.
Yeah, so if you added a product in, I don't know why you would, it would try to take it away by favouring the reverse reaction. So it's always the opposite to what you're trying to do. Okay? When you've done a few of these, they're actually quite simple. Okay? Would you like us to do an example where we actually favour the reverse reaction? Yeah? So, the way of getting it to favour the reverse reaction is either you add a product or remove a reactant. Which would you like us to do? Add a product or remove a reactant? Add a product. Okay, so the system's at equilibrium. We are now going to add a product. Okay, so the first thing is to say what the effect of that is. So I'll put the thing about equilibrium being lost in brackets now, because that's the whole point. If you're adding something to it, it's no longer going to be at equilibrium because you've opened the system. Okay? So that's the change we've made. Now let's apply Le Chatelier's principle, which says that the system responds by trying to minimise that change, and it does so by favouring the reverse reaction, which reduces the concentration. Yeah? Now this might actually confuse me. What do you mean by equilibrium shifting to the products? What it means is the concentration of reactants is going to go up, the concentration of products is going to go down. So in other words, you're favouring that reverse reaction. And this is what's going on in terms of the relative proportion of reactants to products. So the product concentration is going down because that's what Le Chatelier's principle is telling us is going to happen. You're going to try and reduce it. That concentration goes down. If that happens, then the concentration of reactants must go up. Yeah? So there's three parts to that. What's the effect of the change? How does the system respond? And what's the effect of that response? So you've got the cause, the theory in between, and the effect. Just like what we did with collision theory and how changing something, just like this, changing something affects the rate of reaction. We use a structure to answer the question. We can use exactly the same structure to answer one of these. And that's what we'll do when we've gone through all of the factors that affect change. So that's actually the simplest one. Concentration is a quite straightforward one. And it nicely introduces you to Le Chatelier's principle. So those three parts to the answer, the change, the effect of the change, Le Chatelier's principle, and then what's the consequence. What we're going to look at next is it's very specific to reversible reactions that involve gases, and there's an awful lot of these. And that's what happens when you change pressure. Okay. Yes?
So like, if you decrease a if you take out a reactant, will that mean that?
So if you take out a reactant, what's the effect of taking a reactant out on that reactant?
It will go down.
What will go down?
There's concentration. Oh,
Concentration. Always in terms of, remember, Casey is always in terms of concentration, so you should talk in terms of concentration. Because we're talking about changes in concentration. So if you take out a reactant, you've decreased the concentration of that reactant. What does Le Chatelier's principle say you're going to try and do?
You're going to minimize the effect of the change.
So you're going to try and increase it back, aren't you? How are you going to increase it back? Yeah, so you basically think in terms of which reaction are you going to favour? Are you going to favour the reverse or the forward reaction? What's going to produce more reactants? Going the reverse reaction? Yeah, so you're going to favour the reverse reaction, and that's going to produce more reactants, and so the concentration of those reactants is going to go back up. So you've removed one, you've decreased the concentration, it favours the reverse reaction, which actually increases the amount there, and therefore the concentration. So if you're taking it away, it's putting it back. Yeah, does that make sense?
Yeah.
It goes without saying, if we're talking about pressure, then we're dealing with systems, reaction systems that involve gases. So I'm just taking a very generalised reaction system where you've got two reactants that are gases reacting together to form a product. Now, before we actually start to explain what goes on when you change pressure, it's a good idea to understand what pressure is. What causes pressure with the gas? What are the particles doing with the container, inside the container? They're sort of moving around and colliding with the inside of the container, aren't they? And the pressure is caused by those collisions. And so, if you want to increase the pressure, for example, there's two ways in which you can do it. You can heat it, and that means that the particles colliding with the wall of the container collide with more energy, and that increases the pressure. Okay, but we're not going to be interested in that because we're assuming that we're going to keep the temperature constant because we're going to change one thing. You can't do a fair test on anything if you're changing more than one variable. Okay, so we're going to keep the temperature fixed, but we're going to change something else. Okay? So what else changes pressure? How can you increase the pressure in a container but keep the temperature the same? How would you increase the pressure in a tyre? You pump more gas into it, don't you? In other words, you put more air into it. So the more air particles you put into a container, gosh, this is hard work. The more air particles you put in, or gas particles you put in, the higher the pressure. Because there's a larger number of particles colliding with the inside of the container wall, and that increases the pressure. So in other words, the pressure inside a vessel depends upon the number of particles inside that container. Should we write that down? Because that's what we're going to use. Okay? So what we're saying then is if you've got more gas particles in a container, you've got more pressure. So those are the two important parts of that explanation. And so long as everybody understands that, everything that follows should be fairly straightforward because we'll take it step by step. Right, if we look at this reversible reaction that's at equilibrium, okay, How many particles are on the left? On the left, in the reactants? 2. Okay? There aren't actually just 2 particles, but say if we have a big enough container, we've got what we call 2 moles. Okay? And don't worry about that, we'll come to that later. What happens if I now push this right to the other extreme? How many moles of particles do I have here? So I've reacted all these away and I've just got this. 1. So I've got 2 moles at that extreme and 1 mole at this extreme. So say they didn't react together, I had 2 moles of it, then I'm going to have a certain amount of pressure associated with 2 moles of particles. Say they then reacted, completely reacted, so I suddenly have half the number of particles there. What's going to happen to the pressure? It'll decrease, it'll do more than that. You can be a bit more precise, it'll halve. So say we're now at equilibrium with this thing. Okay, doesn't matter where it is. And we suddenly increase the pressure in the container. See how we can do that in a minute. What does Le Chatelier's principle tell us that's going to happen? What does the system do? It's going to try and reduce it, isn't it? Minimise the effect of that change. We've increased the pressure. It's going to try and reduce the pressure. How can it do that? How can I reduce the pressure in the container? What did we just talk about? You make more products. So you favour the forward reaction. It reduces the number of particles in the system to fewer, and so the pressure goes down. So you increase the pressure, it's going to try and reduce it. And the only way it can do it is by favouring a direction where there's fewer particles formed. So we're getting rid of particles, so there's not so many collisions, and the pressure goes down. And it's the way it works. So there is a provisor here. This will only work if the number of particles on one side in the equation is different to that on the other. If they're the same, so if you had 2 going to 2, no changes in pressure, any form of change of pressure will have no effect on the system. So you have to have a change in number of particles. Do you want me to go through that again?
Yeah.
So the first thing is to look at this equilibrium. At one extreme, you've got twice as many particles in the system, okay, A and B, that's 2 times, as if you were at the other end where you're going to have only 1. So going this way produces fewer particles, and the effect on pressure is to reduce pressure, because you're going from 2 to 1. If you're going this way, then you're going from 1 to 2. So you're increasing pressure. So if you favour the forward reaction, you reduce pressure. If you favour the reverse reaction, where you've got more particles formed, you're increasing the pressure. When I say favouring the forward reaction, what I mean is that that rate is faster than that rate. So you're producing more reactants than reactants are producing. So you're producing more products than products are producing reactants, because there's still 2 reactions going on, but the forward one's going faster than the reverse one. So it's being favoured.
So more products.
So overall, you'll find that the concentration of products goes up. Yeah? So favouring it means you're doing more of this than that. Yeah? So favouring the forward reaction, what that means is 2 particles go to 1 particle. So you've got A plus B, that's 2, but only 1, which is C. Okay? That has the effect of reduces the pressure, because reduces the number of particles in the system. So that's the important thing. The forward reaction, favouring that, means that we will reduce the pressure. The important thing is favouring the reverse reaction increases the pressure. With that on board, we can just apply Le Chatelier's principle. So how do we increase pressure? Well, generally, either you've got a fixed size vessel and you pump in extra reactants or products, and that will increase the pressure. Or the easier thing is you've got your system at equilibrium in a vessel and you halve the volume of the vessel. What does that do if you halve the volume of the vessel? Does it increase or decrease the pressure? It increases it, because if you think of a bicycle pump, when you do that, it increases the pressure and it expels air from inside the pump. Yeah? So decreasing a reaction vessel volume, which is the standard way of asking such questions, is a way of increasing the pressure. So if you double the volume, but don't add anything into it, then that decreases it. So we'll do that. So we'll put that there. Okay, so we're going to use Le Chatelier's principle, and we'll do this, then you can have a break. Okay. So using Le Chatelier's principle, with all this information, what do you want to do? Do you want to increase the pressure or decrease the pressure? Decrease it. Let's do something that's sort of the opposite to everything we're doing. We've always been making things bigger, haven't we? Let's do something where you're making it less. There's one final thing to say about this. So this is exactly the same as before. We're just saying, what's the effect of the change? The change has been we've halved, or we've increased the volume, so we've increased the pressure. That's the effect. The system responds by trying to minimise that effect, okay, and does so by favouring the reaction direction, which minimises or decreases the number of particles, or increases the number of particles in the system. Because you reduce the pressure, you've got to try and increase it back up. Okay? And so that's the response of the system, and the effect is that the concentration of products goes down. Rather than taking the concentration, can I change that to amount? Because what you're doing is you're actually changing the volume as well as the number. So it's getting a little bit more confusing as to what the concentration is going to be. So I'm just going to put the amount rather than the... If you put the concentration of reactants and positives actually changing relative to each other, you expect Kc to change. In fact, what you find is if you change the pressure of a system in equilibrium, it will actually restore equilibrium, and if you recalculate Kc, it will be exactly the same. So just like changes in concentration, changes in pressure have no effect on the value of Kc. And that's the final thing we need to write. Okay, so